Okay, good morning everyone. So welcome to this class. So this class is Semiconductor Physics and Device 1. Although it's a 1, but we will try to cover the most important concept for the semiconductor, especially focus on the device related knowledge, because in the end the physics is a fundamental knowledge that helps us to understand the device operation. But the final goal is that I hope everyone, by the end of this class, you are able to understand the device operation, to understand how we actually analyze one particular transistor. For example, the most important part is the MOSFET. Before we go to the MOSFET, for sure that there are lots of the basic we will start from the semiconductor materials, and then we will start for the quantum physics. And later we'll start to move on, because in the one kind of a semiconductor material is always considered two different carriers that flow, that interact with each other, which is electron and holes. So we will consider how to understand the electron and holes behaviors in the one piece of the semiconductor material. And then in this case we will divide by two different. One is under the equilibrium, which means that we don't give any additional bias. It's only for the static. We don't provide any additional voltage, additional force. And on the other hand, for sure, to really understand the device operation, we need to consider that the material that has electrons and holes, and also under the certain electrical force, under the bias, under the temperature. So how do we understand the carrier behaviors? That would be the very crucial for this semiconductor physics. And later, once we finish this basic for the to understand the carriers behaviors, then we will start to move on for the very simple structure, which starting from the PN junctions, and later we go for the PN diode, we go for the MOSFET, and that's all. That will be the main focus on this class. Okay, so as you may already knew that the semiconductor technologies become necessary to enable many high performance products. So in our nowadays daily life, we already consider that the life cannot be living without all these electronics products. And most importantly is we need this very amazing semiconductor technology to enable our amazing electronic product. So here is two examples. I think that everyone in this room should already be using this kind of the product. So on the left hand side is the iPhone 17. This is the latest version for the iPhone that's already contains as A19 for their core chip here. So if you look at inside of an A19 Pro, then we can have a certain we can understand that inside the A19 Pro, this kind of chip that's already contains 6 CPU. And also we have the 5 GPU. So that's already enabled, that's already realized in the latest iPhones. If you are using the iPhone 17, that you already start to leverage this 6 CPU and then the 5 GPU in your cell phone. So for the iPhone 17 family, and with it comes a new generation of the Apple's cutting-edge smartphone SoC, silicon on chips, and the A19 and A19 Pro, that's a main core chip part for this i17, and with access to the TSMC's latest, that's enabled by the 3 nanometer generation, manufacturing process, and also so far the A19 Prof has already more than 25 billion transistors. So that's also give you a little bit understanding that for the state of our product that you might have nowadays in the daily life, that's already enabled by the latest generation 3nm technology. And also inside the chip, there's already more than 25 billion transistors. And also, this is well known for the iPhone. Everyone knows that there's the latest technology in the iPhone. But on the other hand, also want to share from another very important product is that in the right hand side, you see this is a very simple charger. That's a charger for the iPad. Sometimes we call the charger, or sometimes we call as an adapter. So, in anyhow, no matter what the name is for charger or adapter, charger is the common term that we use for our daily life, 充电器. But in more professional technical term, we call the adapter. But the main function for this charger adapter is mainly to do as a power converting, which means that in Taiwan we have AC 110 volt from provide to our home, and then we need to use this adapter or charger to convert the AC 110 volt to our certain voltage that our CPU, GPU needed, which for example is a 1.5 volt for DC. So that's the main function for this charger adapter. And because of this charger adapter is considered doing as a power converting, we convert the energy, electricity from the AC 110 volt to DC 1.5 volt. So we also call this as a converter. So inside us, this very simple charger, charger that already have the very important function, especially for doing as electrical converting. Because of even you have the latest generation of the iPhone, as you know that if you try to bring your cell phone all days, if in the end you run out of your battery, you cannot do anything without your cell phone. So in the end, the charger or converter is also become as a necessary technology to enable our product. So here is one example for this iPad charger, which is the function is doing as a AC 110 volt to convert to the DC 1.5 volt. And if you look at the schematic of inside this iPad charger here, this is inside of this charger. We see the lots of component on bonding on this PCB board. But if you try to look at the detail of the circuit as a schematic showing here, so this is a circuit schematic for this converter, for this charger, and we can start to see inside this the charger there are many semiconductor technology we need to understand. For example, we have here, if you have already followed the basic electronics in the undergraduate, you should familiar with the symbol of this S1. So this S1 is a typical transistor. And also, in addition to the transistor, we also need this one. This one is a diode. So that's why that in this class we will talk about the transistor. We'll talk about the diode, because these are the two main important components in the many of the circuit, in the many of the chips. And of course, inside the diode is enabled by using as a very simple PN junction. So once we put a P-type semiconductor and the N-type semiconductor material put together, then we can start to have this very interesting physics will be happening between the P and N, and therefore that will create a certain very interesting characteristic that's for this as we call as a diode, which we will talk about later. And in general, in the scope of try to understand this charger and then inside of this power converter technologies, generally we call as power electronics. Everything that we deal with power converting, that's what we call as power electronics. That's what we call as a field inside of the power electronics. For sure, the power electronics is not only limited for the charger for our cell phone, but also, for example, for the EV car, for the electrical vehicle, we need to have lots of the phase onboard charger or phase charging technology. That also need a very high performance of power electronics. And inside the power electronics, the main component to enable this high performance power electronics is that we call as a power semiconductor device. And then, for sure, in this class, we will not talk about in the circuit level, how these circuit operations that enable this for the high performance logic, for high performance power converter. But in this class, we will mainly focus on the fundamental for the IV characteristic for the device that we are interested in, especially when we talk about the IV characteristic, as being the engineers like us, as being the semiconductor engineers like us, what we actually really interested in is always the current versus the voltage characteristic, and which more specifically we are interested in as a IDVG. That's a drain current versus a gate voltage, and also IDVD characteristic, which later we will explain. We will explain what is the IDVG and IDVD and why these two characteristics are so crucial. If you try to look at the certain academic paper that you can find in the internet, most of the academic paper, when they talk about the semiconductor device, in the end they always would like to show us the IDVD or IDVG, because that's a very important characteristic that we can understand how good or bad this semiconductor device can be. So if you try to look at further how this technology development from the early time until right now, we have seen there's many very fantastic ideas that have been bringing in the academic in the end to realize in the industry, in the end become our product. So here, this is the slide that's coming from the TSMC, the previous President Mark Liu in the IACC 2021, as he showed as an industry roadmap coming from the mindset, coming from the TSMC. I think this is a very nice summary to let us understand how this technology evolutions from the early time until right now. So from the 2005 to up to the around the 2012, this is a generation that we call the 45 or 28. At the moment, the main technology breakthrough to enable this advance of our semiconductor which is based on what we call as the equilibrium scaling. So the equilibrium scaling, that means that we try to make our transistor as smaller as possible in every possible way. We try to scale down our dielectric thickness. We try to scale down our channel length. We try to scale down our pitch size. That's how we call this equilibrium scaling. We will also talk about this equilibrium scaling later when we talk about MOSFET. But this just to let you know that in the past decade, we have so many innovation, but in this innovation is always first to be proposed in the academics and later to be realized in the industry. So this just also an idea that let you know that what you learn from the semiconductor professional, what you're doing for your thesis, actually that's very important. It's not just a paperwork, it's a technology that might be enabled, might be realized in the next 10 years, in the 20 years. When we talk about the semiconductor professional as a graduate student, no matter you are as a master or PhD student, you don't have to worry that what you are doing here is just a paperwork. It's not actually just lots of discussion that are being published in paper, because all this discussion in the end will be realized as a technology enabled for the future. So this is just one example for the equilibrium scaling. And how do we make it as this equilibrium scaling? What we actually trying to do at that moment is mainly introduce as a high K metal gate, and also we introduce strength silicon. Because of this one, we can start to make our transistor as smaller as possible. That's we call as a equilibrium scaling. But once we try to scale down everything, in the end we'll reach a certain physical limitation, which means we cannot make as a thinner anymore. There's some physics we will talk about later, why we cannot make our semiconductor material very thin, very small anymore, because in the end there's a lot of non-ideal physics phenomenon will happen that make that we cannot control our transistor perfectly. So therefore, we need to have new innovations. So starting from the early, around like the 2012, we start to have the new transistor structure. New transistor structure. And also the new materials. So we start to have these new structures, new materials that help us to enable for the next generation of the semiconductor technology. And here for the new transistor, new material, what I mean here is mainly refer to the breakthrough of the FinFET. And also the new material that means with the breakthrough as we consider as a high mobility channel. Also, because we need to make our transistor even smaller and smaller, we need to precise control the thickness, precise control process. We also need to introduce a new semiconductor process. And then starting from 2012, people are talking about the EUV, which is a very advanced lithography that helps us to enable the smallest semiconductor technologies. So, in summary, introduction of the strength silicon and the high-tech metal gate, and also the FinFET, EUV, and high mobility transistor, high mobility channel that help us to enable to the getting more and more advanced semiconductor technology till so far until the 5 nanometer, even 3 nanometer here. And also one of the things is very important is that not only for the technology and process novelty, but we also have to bring the design as a new kind of mindset because of when we talk about FinFET, when we talk about the high mobility channel, when we talk about very advanced transistor, like later in this class, we will also talk about a little bit about the CFET as a nanosheet. All these different technologies that always bring us a lot of issues that are coming from the parasitic. How do we optimize the design? How do we optimize the layout to enable the maxima, the optimize system level performance? So in the end, we are not only needed as a process and then device innovation, we also need this one, what we call the DTCO, which is design, technology, co-optimization. So this means that for people who learn, who understand the semiconductor device, they are actually broad their future career. They are not only working as a device-related foundry, but also the circuit level, the system level company, they also need our expertise. Because for the circuit level, for the circuit people, for the system people, what they are trying to design for the circuit is not the typical planar MOSFET. It's a very advanced FinFET, it's very advanced CFET, and so on. Even we have lots of new materials coming. For example, we have a ferroelectric, we have a wide bandgap compound semiconductor, we have a 2D material. But all this material will bring us a different kind of consideration of the design. So that's why if you look at as an industry recruitment for the new vacancy in the circuit company, you will see that they also start to recruiting, getting more and more for the people who understand this new technology. So that's also give us a new kind of the horizon and then the new future. We are not only working in the technology side, but we can also working on the circuit side. So with this all the innovation, that's why we can bring us up to nowadays to help us to get us to a 5 nanometer technology. But for sure that beyond this, we have another very additional technology that will still needed. For example, in here, this is the roadmap up to the 2030, and then we have a theme. There's so many innovations happening here: 3D FinFET, low resistance barrier, and also we have this one, metal oxide, and we have the EUV and even the new channel material. So still, with the technology evolution, we need getting more and more innovation and breakthrough to keep us to keep this industry can follow this industry roadmap. And then as we expected from the 2020, we will start to foresee there will be more 1 trillion transistor in the single chip. That's a very incredible large number, but this all coming from the effort from the last several decades, because all this great innovation, that's why we can bring us to the today. That's why we can enjoy our many fantastic technologies. So here is just show you some of the latest paper, and then also just give you a certain idea that from this class, by the end of this class, of course, you will be very difficult to understand every detail, but at least you can get a little bit rough understanding what is the latest technology about. And then this is a paper that published in the IEDN 2024, which is the latest detail that the TSMC reviewed for their 2 nanometer technology here. So if you look at this title for this paper, is a 2 nanometer platform featuring with energy efficient nanosheet transistor. So now you can see this is just a 4th slide that we talk about, but there's already several terms probably is getting repeated on your mind. First of all, for example, we already talk about 2 nanometer. Also, we talk about the transistor. I guess maybe around 60% or 70% of you at this classroom have already followed the basic semiconductor for undergraduate, but they might be around 30% didn't have no idea what is a transistor here. But it's fine. We will talk about later, but as you can see, this is the 4th slide. It's a key term is already coming again, which is a transistor. And of course, there's a certain more complicated, they say this is an interconnect called optimization with a 3D IC for AI, high performance computing, and mobile SoC application. So when we try to read, this is an academic paper published by TSMC. So this is also just a good reminder that when we read the paper, don't think about this is just an academic. Some people might think this is useless. They say that this is just an academic paper. It doesn't make sense. It's just a pure theory. But you see this, the top semiconductor company, they also publish a paper. Why they have to publish a paper? Because they want to showcase their technology. They want to have the chance to let the people understand what they are doing. And then this is a 2 nanometer is not ready. It should be ready for production in the next 3 years. But in the 2024, they start to show certain progress on this 2 nanometer platform. That's also indicate as a confidence for the all in the field, in the semiconductor field, that the technology can always continues advance, and there's no barrier as long as we keep working on this, as long as we keep investing our ideas and efforts. So when we read this paper, as most of you are new to this graduate study, my advice for try to understand the paper is always look at from the abstract, because from the abstract you can always already quickly get a sense what this paper is talking about. So in the first sentence of this paper, a leading edge 2 nanometer CMOS platform N2 has been developed and engineered for the energy efficient computing in AI, mobile, and HPC application. So if you try to read the first sentence, you should be able to get a sense that the first sentence, this sentence, actually just a little bit expand and refresh of the title. What this sentence trying to tell us is exactly the same like this title, right? So the title saying 2 nanometer platform for 3D IC for AI, HPC, mobile SoC, but the first sentence for abstract is exactly the same, trying to illustrate the same main point, just like the title. So this just also want to let you know that when we try to write the paper, you don't have to read a phrase, it's very complicated. What we try to write the academic paper, we just try to write it as clearly, as simple, as most people can quickly understand. And then sometimes we just keeping refreshing, keeping saying the same main point, just to remind the reader or the worldwide researchers that what this topic is talking about. So the first sentence of the abstract is always as a kind of a reference of this as a titles here. So let's just quickly go through what this abstract is talking about. This leading N2 logic technology feature with energy efficient gate-all-around narrow sheet transistor, middle of line and back end of line interconnect with a density SRAM up to a certain number. The N2 deliver a full node benefit from previous 3 nanometer, offering us a 50% speed gain, 30% power reduction, and also the chip density increase around more than 1.15 tons. So that's a main advantage of this 2 nanometer technology. But also this can be one of the typical example that we can learn how to write the academic paper. So in the beginning, we always bring as a certain introduction to break through to mention what we are doing, and later we will start to talk about certain details. Right? This is the details. How these details outperform from previous technology. This is why the typical way we write the paper. First, we will mention as what is a general goal, what's a general topic, and later we will start to emphasize that this paper is outperformed for the previous work. So this is also a typical typical academic writing way that when we try to illustrate a certain technology here. So the rest you can read it by yourself. I will not go for detail because the rest is many technical detail might not be explained in this class, but with the time passed by, you will get more experience and you will understand. But also the right hand side, the figure is there are many figures in this paper, but I just bring out the most important two. The reason why I bring these two figures inside this one, because this is the two important characteristics that we have mentioned that every semiconductor engineer should be pay attention to. For example, the middle one, which is IDVG. So the y-axis is a drain current, and then the x-axis is a gate voltage, right? So this is something that I have been mentioned in a couple slides before, that the IDVG is always a key characteristic that we are interested in. And furthermore, IDVD. So the y-axis is a drain current, and then the x-axis is a drain voltage. So the IDVD is also the key characteristic that we are interested in. Of course, inside this paper, there are many very great breakthroughs, but I just bring these two because these two are most related to the semiconductor physics and device. In this class, we will again to talk about how to understand the IDVG and then the IDVD. And also, in this two figure also has several interesting characteristics that we will also talk in this class here. The first one, as you see here, this is a NFET, that's an N-type transistor. We have the PFET, that's a P-type transistor. So once we combine as a NFET with a PFET together, which is a technology we call the CMOS. So this is typical for the CMOS technology. We try to have this NFET and PFET together. So also the CMOS is mentioned in here. 2 nanometer CMOS platform. So that's why when we see this CMOS platform, we expect to see certain characteristics that are both combined as the NFET and PFET. And also, on the other hand, there's a very crucial characteristic here, which is this one we call the debol and also the swim here. So first of all, let's try to understand what is a swim. And then before we understand the swim, we need to understand the slope here. The slope of these regions that we call, this part is we call as a substrate hole region. We will talk about this when we talk about MOSFET, but this just let you get a certain idea that when we progress to the MOSFET, we will talk about the substrate region, we talk about the substrate suite, and then the purpose we will illustrate to let you understand, because in every advanced technology, we are very interesting for this slope here. This is what we call the substrate slope. And then this substrate slope, the figure merit for this substrate slope is what we call the swim. It's what we call the substrate swim. And this substrate swim has a different abbreviation, and most of the common abbreviation is SS here. But in this paper, they use SWS, but in anyhow, it's indicate the same thing. That's SS is a substrate swim. So ideally, for the substrate swim, for the typical silicon technology, the minima for the SS is around 70 millivolt per decade. And we will talk about why later. That's always the gold standard, the ultimate goal that every semiconductor engineer want to try to achieve. We want to fabricate the transistor close to the 70 millivolt per decade as possible as we can. And why this paper, they show the 68, because they want to demonstrate that with a 2 nanometer technology, they are enabled as a below 70 millivolt per decade. So that's actually the very good result here. So this is a substrate swim here. And also another very important figure merit here is what we call the debol. And then the full name for this debol is called the drain-induced barrier loading. And this is a very crucial phenomenon when we try to fabricate the short channel device. When we try to scale down our dimension, it's very often to see this debol effect. And then in this paper, they also demonstrate that debol is well controlled around 30 millivolt or 24 millivolt, which is very, very small. So that's also one of the indications this 2 nanometer platform can achieve the very great performance, not only for the system level performance, but also for the typical IDVG characteristic. We can already see a lot of performance improvement here. Okay, so when we try to understand the state of our technology, let's back to the course, this course. Let's back to the goal for these classes. So the course description is that the demanding of the new application, such as 5G, AI, cloud computing, also the electrical vehicle, all these new application trigger the new innovation of the semiconductor technologies here. So the bottom is one of the slide also, but it's a little bit old, but this is also the slide coming from TSMC. This is advanced CMOS technology becomes the key enabler for the innovation. For example, for the 28 and 16 nanometer, that's very crucial for the smartphone. And then 7 and 5 will be very crucial for AI and 5G. But you can see that when we try to understand the TSMC roadmap, that's also, it's a great indication for the future. This is a slide in the 2019. Now it's 2026. This is 2019 data, and then now it's 2026. So from the 2019, TSMC already have the customer request to fabricate the advanced semiconductor chips. That's for the AI. If you look back to the 2019, nobody know what is the AI. Nobody used the GPT was booming after the COVID. So that was a huge booming after the 2020, 2021. But with the request of the customer, the TSMC already has a certain roadmap to enable the new technology for the AI. So that's 2019. So sometimes if you try to look at it as an industry news, try to understand the kind of the new information shared by these leading industries, that's also one of the indication for our future as well. So the right hand side is a typical semiconductor technology we needed inside the EV. This is inside of the electrical vehicle. Inside the electrical vehicle, we need a lot of semiconductor technology to enable. For example, this is an onboard charger. We have the battery management. We also need the semiconductor to drive the car. Also, the power converting from 12 volt, 48 volt, or even for the high voltage load here. So these are the cannot make it if we don't have the proper high performance semiconductor technologies here. So this is why this is the reason why we have to sitting together in this classroom to let you understand what's the fundamental for the semiconductor physics and device. Okay, so the core knowledge of the state-of-the-art semiconductor technology is semiconductor physics and device. So that's why we need to start from the fundamental to let you understand what's the basic physics and what's the basic device structure. And once we understand this, we can use this knowledge to understand the advanced technology. So this semiconductor physics and device is essential for every researcher and engineers. So in this class, the property of the semiconductor material, we'll talk about the basic material property, the physics of the carrier drift. When we talk about the carrier, that means we talk about the electrons and holes, and the operation principle for the most important device architecture. We will not immediately to introduce a very advanced one. We will starting from the basic one. We're starting from the diodes. And then we will move on to the MOSFET. And then we'll move to the BJT, which is a bipolar junctions transistor. And also we will tap a little bit about the JFETs here. So we'll be introduced and discussed in details here. And also, I hope we have time to talk about a little bit more beyond this basic one. So I hope this, if time is allowed, we will also talk about the FinFET, CFET, and so on, because this is a technology happening nowadays, also in the next 10 years. So I hope we have time in the last part of this class. We will also bring some basic introduction for the FinFET, CFET, and so on. But still, if you want to understand this advanced one, it's always good to come back to a basic one, because this advanced just a kind of like the new structure, but the basic idea is following the similar in the conventional one. So what is a diode? So the diode is a piece of the semiconductor device that both have the P-type and N-type together. So we try to bring as a P-type and N-type semiconductor we put together, and that's what we call as a device, as a diode here. So what does it mean for the N-type? So the N-type means this is a material that full of electrons. We have a higher electron concentration than the whole concentration. We call this as a N-type. So what does it mean, the P-type? This means this is a material that has a higher holes concentration than the electron concentration. So that's we call as a holes. So if you try to put as a P-type material and then the N-type material put together, try to connect these together, the most interesting place that has a certain amazing physics happening must be in the region of this connection region, right? So therefore, that's why if you look at the semiconductor physics textbook, there's always a chapter talk about the p-n junctions. So we have to first to understand the p-n junction, and later we use this knowledge to expand as a diodes. So you can see that if you look at the outline for this textbook, no matter what kind of textbook, it's always starting from p-n junction and later go to the p-n diode, because p-n junction, this region is one that has amazing physics happening. So that's a diodes. And another very important device that we will introduce, which is the MOSFET. So the typical device architecture for the MOSFET is look like in this. First of all, we have the certain substrate. Most of the time, we use a P-type silicon as an example, as a substrate. So this is what we call the substrate. And inside this substrate, we have the, on top of this substrate, we have the dielectric. And then the most, of course, if you look at the advanced technology, there are so many different dielectric, but in here we go for the very fundamental and most widely used, which is the SiO2. So we have the silicon dioxide here. And then on top of silicon dioxide, we have the metal. So here we have the what we call the gate metal. And to complete the MOSFET structure, we also need a certain N plus region where we have the N plus here and N plus here, which is N plus here. In this class, we will use a lot of MOSFET as an example to let you understand. We will not talk about MOSFET until the chapter of MOSFET. We will bring the MOSFET from the beginning till the end. We will use a lot of MOSFET for the example because the MOSFET is a very crucial structure that everyone should try to understand, and then many good example and physics can be also understand by using the MOSFET structure. For sure, this is your first time to look at this device structure. You might be confused, but it's fine. If you listen first time, you don't understand, but we will continue to repeat again 10 times, 20 times, 100 times. In the end, the MOSFET, this kind of device structure will become as a typical impression in your mind. Then you won't feel any weird about this structure because in the end, this is a MOSFET. So, but still we have to explain why we call this as a MOSFET. Because we have the metal here. We have the oxide. We have the semiconductor. So, therefore, the first letter for this metal oxide semiconductor, we just call as a short as a MOS. That's why the MOSFET has a name of a MOS. But the full for the MOSFET is called the metal oxide semiconductor. But the FET, what does mean the FET? If you look at the TSMC 2 nanometer paper, they also talk about the NFET and PFET. So what is FET? So the full name for FET is a field effective transistor. So that's why we call this structure, this device, we call as a MOSFET because of the full name for this is just way too long. Metal oxide semiconductor field effective transistor. So we don't call this again. We just put it as a short name, just like our nickname. So the nickname is MOSFET. So that's why we call this as a MOSFET. And also this is one example that I think in this class we have around like the 30% of our international students. We have 70% for local Taiwanese students. And of course, I can fully understand for the local Taiwanese student, we prefer to read, to find some Mandarin textbook. Especially when I was a undergraduate student, I also try to find some Mandarin textbook to understand the semiconductor physics device. It's called like the 半导体物理元件. But I get so confused about the name, the translation of MOSFET, because the MOSFET is a translation into the Mandarin, just called the 金属氧化物半导体场效电晶体. Sometimes we call as a 金氧半场效电晶体. Actually, you won't get further understanding, even you try to translate the Mandarin, because it's just a translation. It doesn't have any meaning that you can get a further deep understanding when we translate to the Mandarin. So that's why in this class, I suggest that many of these professional terms, just forget about the Mandarin. Just use this term, MOSFET, because this is just a combination of the structure. If you try to memorize this device schematic, you won't get confused what does mean the metal oxide semiconductor, because it's just description from top to the bottom. That's why we call it MOSFET. Later, we also have a bipolar junction transistor. We have many different kind of the transistor. If you all want to understand from the Mandarin perspective, that will get you way too confused. Just try to memorize the device schematic and try to understand why we call this structure as English, because the English name, why we name this as a MOSFET, from the top to bottom is a metal oxide semiconductor. But also here I want to explain furthermore, why call this as a field effective transistor? When we talk about the field effective transistor, for sure, when we talk about the field, the first things come to our minds, it must be some place we can provide the bias. Because once we have a voltage bias, that will create the electrical fields here. So inside this MOSFET, in the most of the time, we will ground it in this region. This is the region in the left-hand side that we call as a source. Sometimes we just put it as a VS. This is the bias, the voltage we apply on the source side, we call the VS. And then on the right-hand side, this is a region we call as a drain. And then the bias we put it on the drain side, that we call as a VD. And because right now the MOSFET is a 3-terminal device, we have a 3 places that can apply the bias. We can apply the bias from the source side, we can apply the bias from the drain side, but also we can apply the bias in the gate side, because gate is a metal, so we can apply the VG here. Also, that's also the one example. If you try to look at the Mandarin translation of the source, drain, gate, you just get confused. The drain typically we call it 极极, the source we call it 原极, and the gate we call it 杂极. Of course, if you have around like a 2 or 3 years experience in semiconductor, you can finally get through understanding why it's called the 原极, because this is the region where the electron is provided. It's a source for the electron. And the drain means a drain away. That means that the electron is providing here and flow to the side. That's what we call the drain. But anyhow, we will talk about this later. So once we know we can apply the bias from the gate side, we can apply it from the drain side. And let's start to imagine if we try to continue to increase the gate bias. Because right now I want to let you get a brief understanding what is the IDVG curve. As I say, the IDVG is always the most crucial characteristic that we are interested in. So right now, let's just step by step to understand what is the expected IDVG characteristic. So if you look at this IDVG characteristic, the x-axis is a gate bias. So that means if we continue to increase, continue to consider as a right direction, that means the gate bias is increased, right? This direction suggests a gate bias increase. So once we have this gate bias increase, what the phenomenon can be happen? This is a positive bias. This is a high school physics. If you have a positive bias on the one side, for sure you will start to attract the electrons, right? Electron is a negative charge. So the electron will be attracted by the positive bias. So therefore we can expect we have the electrons being attracted in this region. And also, one thing I want to mention, this is a dielectric, which is insulator. So if you follow the Newton physics, that's where we learn from high school, this carrier, of course, when we talk about quantum physics, we will have a different phenomenon. But consider for the Newton physics, this electron will be blocking below the dielectric, but we continue to increase our gate bias. So therefore, we can expect the increase of gate bias can cause certain attracting electrons below the dielectric, right? So that's what we can expect as we increase the gate bias. But on the other hand, also want to be reminded that the drain bias is not the 0 volt. Normally we put this as a grounding, so this will be 0. But this one we will provide as a smaller bias. For example, positive 1 volt. So imagine if you have the positive 1 volt on the right hand side, this electron will start to flow to the right, because of the top side is blocking by dielectric, and therefore you have the positive bias on the right hand side. So for sure the electron will start to flow to the right, and that will become as a drain current. So therefore, with this kind of understanding, that's enough to help us to get an expecting IDVG curve. So the normal IDVG characteristic is, first of all, the gate voltage is not larger enough. So there are not enough electron accumulate here. So once we increase the gate bias up to a certain voltage, the electron accumulator is large enough, but at the meantime we have a drain bias on the right hand side. So we can start to see the current. This is increase. And this is a consideration of VD equal to 1 volt. So that's all. That's how MOSFET operation, if you can follow my explanation. Of course, there are several. This is the most simple one, very simplified physics to let you understand. Of course, there's a certain much complicated physics beyond this one. But at least this is a very good starting point to let you understand why the IDVG curve will become like in this way. So let me illustrate again. When we talk about the MOSFET, it's always considered as a metal oxide semiconductor. But we also have the source and drain in the right and left hand side. And most of the time, the source will be grounded and drain will provide us a small bias here. And once we increase the gate bias here, we start to attract getting more and more electrons in this region. And this region is sometimes we call as a channel. So, but beyond the certain gate bias, these electrons are larger enough. And in the meantime, we have the drain bias here. So the electron will be attracted from left to the right and become the drain current. Become the drain current. So that's why this is a typical IDVG characteristic. But to understand the turn-on region, as I say, we are very interested in this turn-on region. And then most of the time, we will plot as a log scale. We plot log ID versus VG. And then we will see this graph will become like this way. And now, if you back to the TSMC 2 nanometer paper, this is exactly curve they are showing me here, right? So that means ideally it's not difficult to understand why the IDVG will look like here. This is also under the small bias of VD, and this is a turn-on transient. This is a log ID, so we can start to see after a certain moment. If you this is log scale, if you try to plot the linear scale, this will be also similar, like here. So this is how. That's why the MOSFET is a very important one, because of TSMC 2 nanometer paper is talking about the nanosheet, which is a structure that even very difficult to draw. It's very difficult to use to have the hand drawing for the nanosheet. But the fundamental physics operation principle is the same as a MOSFET. With this simple MOSFET structure is enough to understand the operation for the FinFET, for the nanosheet, for the CFET, and so on and so on. Also, in this class, we will also talk about the BJT. The full name for BJT is called the bipolar junction transistor. And why we call this as a bipolar? If we need to understand the bipolar, first we need to go back to the MOSFET. The MOSFET is mainly operation consider the electron flow in the channel. So which means this is what we call the one carrier dominate as a current. One carrier dominate the whole transport characteristic. So that's why the MOSFET sometimes we call as a unipolar. This is we call the unipolar transistor. The unipolar, uni means a one. So that means a unipolar means that the inside the MOSFET, the main transport characteristic is only dominated by one carrier. In this case, it's an electron. But what does it mean a bipolar? Bipolar means a double. Bi means a double. So that means this is a transistor that being involved as electrons and holes. That's why we call this BJT, bipolar junction transistor, BJT. And if you look at some of the Mandarin textbook, they call it 双载子. Why we call it 双载子? Because 载子means a carrier. So that's why we consider electron holes at the same time. That's what we call it BJT. And what is the structure for this BJT? It's also very simple. It's not that difficult. If you can understand the MOSFET, it's the same. If you can understand the PN diode, it's exactly similar to the PN diode. But now we have the two back-to-back junction. We have the P, P. So we have this two PN junction here. That's with this structure, we can make it as a bipolar junction transistor, and which we will also explain this later. And in this class, we will use mainly use a MOSFET as an example to understand, because the BJT is very important in the early time, but later it's become as a very niche technology for a certain application. But MOSFET right now is widely used in the logic, analog, power, whatever. That's we always need the MOSFET. So we will prefer to use a MOSFET as an understanding. Okay, so furthermore, in this class, we will also talk about the recent progress and challenges in developing beyond Moore's law technology. So if you try to understand what does it mean beyond Moore's law, first we need to understand what does it mean the Moore's law. We will talk about the Moore's law later, but the ideally for the Moore's law is just as a empirical prediction, as a transistor will getting smaller and smaller, and the density will improve and improve as a certain timing, and therefore the technology that we follow in for the Moore's law is sometimes we call, as shown here, Moore technology. So in the sense of a Moore technology, what we are doing is doing for the scaling. So from the early time 19 nanometer until so far 5 and 3 nanometer, these are the technology in the category we consider as a Moore. But on the other hand, there is a technology that beyond this scaling, we don't have the warrior scaling, is mainly for the interacting with people and environment. That's the technology we call the more than more. For example, the RF technology, that's in the category of the more than more. The power device, the sensor, the biochip. In these technologies, we don't have to worry about scaling. We are more worried about the functions that these technology provide, where it's able to interact with the people and environment. Also, in this class, we will follow this 6th level of this Bloom for the education. Also, this is good for you to evaluate yourself that when you try to learn the new subject, learn the new things, always keep in mind there's a 6th level of the different learning. Of course, in the beginning, this is a remember, and remember is not the key. It's not the most important for this one. In the class, we hope to, from the remember, elevate it to understand, to apply, to analyze, and to evaluate. So that's how this class will try to organize up to the evaluate. Of course, it's difficult for this class to have the chance to allow you to have a create, because create needs a certain of the experimental task. But in this one, still still will be the in-class lecture. So, this is also good reminder that when you try to learn the new subject, always keep in mind that follow this different level that will help you in the end to work in the case, in the sense of creativities. So this course will be designed based on the constructive alignment. So in the sense of a constructive alignment, we have 3 different pillars in the end to design these classes, and also to have a certain practice in this class. So we have 3 different goals. So the first one is that we have what we call the intended learning outcomes. This intended learning outcome is very important because this is a goal that in the end, by this class, what you will learn. What you will learn. So we set as what you will learn as a goal to design this class. And next slide we will show what is the intended learning outcome. To support this intended learning outcome, for sure we have some other activities. These 3 pillars will be basically support each others. So therefore we have this teaching activities. We have the assessment task. So this is how this class will be organized. So we will first to list what will be the learning outcome you should learn by the end of this class. And based on this learning outcome, we design for teaching activities, we design for the assessment task. So the first one, by the end of this class, you should be able to explain the basic material property and device physics, that for sure. This is the most basic and most crucial one. And also apply the device physics to evaluate the operation principle of the PN diodes, MOSFET, BJT, and JFET. That's also very important because now you have to level yourself a little bit higher to leverage your knowledge and start to evaluate these different operations in the different device. And also evaluate the current issue in the scaling technology, for example, the more technology. So we will talk about the short channel effect, ultra-thin dielectric substrate switch, and so on. That's all the key issues right now for the advanced technology. And then in the end, once you are able to identify the problem, you are able to propose a design to overcome the challenge in the scaling semiconductor technology. And this is also a very good reminder that what does mean the innovation. There are many good definition for innovation, but the most practical one and most simple one is that the innovation is just matter with problem solving. So as long as you can solve any of the issue in the semiconductor technology, that's already as an innovation. I believe for your thesis, for your graduate research work, is also you will be asked to first to review what was going on, and second, identify something that not has been happened before or something still remain as an issue. That's identifying the problem. And then the next is try to have the innovation for the problem solving. So once you solve the problem, you are already in level of the innovation. That's how this industry prefer for our graduate student in the future. Once you work in the industry, what you want to get a high salary pay, for sure you need to pay a lot of effort to do the problem solving, which is very crucial for the innovation. And in this class, we use this Neiman as a textbook. There are many good textbooks, but I prefer to use this one as a simple and basic one because this one, to be honest, I think is already quite enough for everyone to get around certain professional in the semiconductor knowledge. For myself, that I tried to read this one when I was undergraduate, and then I also still use one as a graduate student. And nowadays, I still use this one to time to over review the chapter in this one. This one is good enough. Of course, there's another very famous one from the Professor Simon C. But I will consider the Professor Simon C's books as kind of like a dictionary. That means it contains everything, every detail. But every detail is not good for the beginner, because sometimes you will get confused why we have to learn this. Because in the Professor Simon C's textbook, they try to explain everything in the detail, and sometimes just you will get lost, and then you will always. Therefore, I suggest that try to starting from this one. If you get something not very clearly, you can try to look up. Nowadays, there are many online resources. You don't have to immediately look at the Professor Simon C's book. You can look at lots of internet resources. You can even ask the GPT. They will definitely help you to answer your questions. So every chapter, once I finish, I will share the lecture notes for everyone. So if you don't have time to take a note, you don't have to worry. It's good time that you can review. Later, I will upload in the lecture note. I think in this class, I believe many of you have already followed. Some of you have already followed my classes before, and some of you have been seeing my lecture video on the YouTube. So I will share all these lecture notes. I will also upload all the videos. So you don't have to worry. You cannot follow the progress, because in there it's good time for you to review again. And also in this class, we will introduce some basic band diagram software. You will have the chance to practice, but that will be close to the end of the semester. And because of now, I guess we have more than 120 students, and I believe that during the break, there's some more students will want to sign up. For this one, I'm actually pretty welcome for students who are interested in this class, and they are all welcome to sign up for this one. Even you are from undergraduate, even you are from non-semiconductor professional, because my goal for this class, I just want everyone to understand that try to understand the semiconductor physics and devices is not that difficult. There are many professors use a different way for lecture, but my goal is I want to make this as easier that everyone can understand, because if you can understand, you will get the inspiration, you will feel more interested in on this technology. But if sometimes we just lecture way too complicated, we focus on too much physics, we focus on the lots of equation, some of you might prefer, but I guess at least 70% or 80% of you might get lost. Why we have to learn this equation? So my goal is I want this class to be the simple, and then everyone can digest in your own way, that in the end everyone can be inspired by these semiconductor technologies. My previous learning experience when I was undergraduate, I think the reason, one of the reasons I choose the semiconductor or solid state as my professional is because of I always remember in the first year of my fresh, I followed the computer science class for the C++. And I think the professor didn't lecture very well, so I didn't understand what is the course about C++. And then finally I feel like I just cannot understand everything. I cannot follow. This stopped my interest in this computer science domain, because at the moment I was a fresh student, so I just feel like, this might be, I don't have this talent to understand. The professor just lectured way too difficult. I don't have any sense to understand. So that's actually completely stopped my interest. But that's why I don't want this class to be the stopping point for everyone. This class should be the new gate, new window for everyone being entered in this semiconductor industry. So that's why that we have many students here. So that's why we have the 4 TA, because they will have a lot of loading to do the course grading, and also they will have a lot of loading to help everyone. And also, we need to have this phase group. So that's a very important one. This is a phase group that for the student who follow this class. So you can use this QR code, and there's several questions, because I don't want the student there's some student who watch my YouTube, and then in the end they want to access to the Facebook, but I want to understand that a little bit about your background. So there's several simple questions, where your university of department, your name, student number, and then also the enrollment status. That also will help me a little bit more easily to follow that the student in this phase group are the students who are really interested in this class. And then the reason that I set this Facebook is because of I will only share the lecture notes. And recording lectures. So all of the recording lecture and lecture note will be shared in the Facebook. And the reason why I created is because our E3 is not easy to use. It's not user friendly, and you need a lot of difficult login. And then just sometimes feel like it's a little bit waste of time to try to figure out how to use the E3. So I decided to run this. But it's good that this can be the platform that if you have any question, you're welcome to ask me later as well. So you need to sign up. You need to be approved inside this Facebook. And also one more thing I want to mention that this is first class, so I'll try to finalize everything about this course schedule and course structure and also the lecture hours. So our original timing for this class is 9 o'clock on the morning, and today is the first day of a new semester. I appreciate that everyone, no matter you come back last night or come back this morning, I appreciate everyone who come here 9 a.m. But to be honest, 9 a.m. is also very early for me. Sometimes I also a little bit suffering. So let's just make a deal to rearrange a little bit. So the total, this is a 3 hours lecture. The total actually, if you consider break, is the total is 150 minutes if you don't consider the break. But so let's just try to reschedule from next week, starting from 9:30, and then we don't have because normal class we have a 2 break, but I think it's not necessary. If you want to have however you want, you can just do it. If you want to go to a toilet, just feel free. If you want to have a breakfast, feel free. So I don't think we need to have 2 breaks. So I just want to have 1 break around 11, and then we will a little bit delay up to the 12:10. And after 12:10 will be the Q&A. But if you need to run for the next class, you need to leave earlier. That's still fine with me. Just let me know a little bit earlier, or just leave, and then because in the end you can still watch the lecture video. Yes. So I believe that everyone should be fine with this. And also one more thing I want to mention, that this is a course plan for this semester. Today is the first day, and then just want to mention that I can already foresee that I will not be available for the certain classes because of I will have a business trip from abroad, so I cannot join the class. So I will still start to, for example, this week. So we won't have a class, but however, there will be the makeup class in the evening. That's at 6 p.m. So I will let you know the classroom. Ideally, it will be the same classroom, but in anyhow, once the time close by, I will let you know. So that's the first one. And the second one is also try to make sure that you will be available on the 6 p.m. on the April 27th. So let's tentatively use that time as a midterm exam. But if our progress is pretty nice, then for sure that I can still use a Monday morning as a midterm exam. But sometimes it might have the problem because there's some progress delay. So therefore, I prefer to not use the time for the class for the midterm. We use the evening, that will be 6 p.m. So just try to save your time, make sure you will be available. And also, there will be another potentially cancellation of the class on the May, and then therefore the makeup class will be the same, the June, the 3rd of June. And also I want to mention that we will have the final exam on 15th of June. So we only have one exam, so I'm not accept for the individual exam. So the reason I announce here, I need you to make sure that you are able to join this exam. If you're not able to join this exam, if you leave home, you go back to your home country, have a holiday. Last semester, I'm pretty surprised that normally nowadays we only have 16 weeks. And then last semester, I think the middle December, is already as the last week of the semester. But as a week of the middle December, many students start to have the winter vacation. I'm a bit surprised because, as you know, the graduate student should not have a winter vacation, right? Yes, so I want to also just make sure that June of 15, at least if you want to have a summer vacation, that's fine, but just after this day. So make sure that you will be available for the June of 15. Of course, if our progress goes smooth earlier, we can probably consider to move the final exam a little bit earlier, like 1 week before, but let's just have the worst case. Let's just have the plan for this worst case. Okay, so in this class we have homework, we have the in-class assignment. That's very regular for the most of the class. So nothing special. And then for the evaluation, the grading policy here, we have the 2 exams that will be considered as 75%. And we have the midterm exam and then the final exam. And then in this semester, I made a little bit slight revision of how you can prepare for the midterm and final. Previously, the midterm exam is a completely closed book. But now, you can bring the 2 pages for A4 to write whatever you want for the note or equation you feel is important. Just wait, yes. So you can bring the 2 A4 pages for your reference. And final exam, if you already heard about this class, probably know that normally the final exam is an open book. And I'm actually welcome everyone to bring all kinds of material. But the problem is that right now the GPT is just way too brilliant. And then most of the time it's just you type your question in the GPT. Even you use a Google search. In the timing that we don't have this AI tool, you can use a Google to search any question you want. But nowadays, you just put as a Google search, the AI already help you to summarize. So therefore, I changed a little bit for final exam. Still will be the open book, but that will be limited by the 2 A4 pages that you can bring down. So that will be the same as a final exam. So we can, in the midterm exam, you are welcome to make your own note and summarize in the 2 A4. You can put any note whatever you want. That can be the reference. And then the final exam, it's the same. Just you can prepare 2 A4, and then during the exam time, you will be only allowed to use these 2 A4 pages. And we have a 50% for homework, and we have the tendency for 10% as well. Okay, so that's part of this class to introduce the typical structure and then the grading policy and all this schedule. So we will start to have the break, and then we will come back at the 10:15. So if you haven't signed up, you can use this moment to sign up in the Facebook. And if you have any question, just free to let me know. So we will come back at 10:15 and start to go deeper a little bit about semiconductor history. Yeah. Okay. Yes.
Question?
Yes.
I'm thinking about like how to study for the exams.
It's a written exam.
Yeah, it is a written exam, exactly. Do you provide like problems?
Yes. There will be the exam sheet with all the problems.
But to study before the exam, do you provide?
Homework. So
the homework is one of the
basic. I think if you are familiar with homework, you will get at least 60 or 70%.
Okay, so the important part is do the homework and repeat the slides.
Yeah.
Because I learn better if I actually get to do stuff like and not only read and actually like to try to do
you can practice.
So it's like homework is the important part.
And then also the example in the textbook.
Yeah, we have similar questions in the.
Yes.
Okay. Perfect. And then for the final exam, as you said, it's the 15, right?
Yeah.
It's okay. It's problematic with my flight home, and I have meetings at my home university.
Yes.
So I can, of course, rearrange. But would it be possible to, for example, put a lecture, an evening lecture, for example, if you go, for example, here, optional class?
Yes.
What if you would put it on the 1st in the evening to then move the final exam to the 8th?
That would be difficult because of then in this case it's very difficult to arrange the two exams because might have the question list issues and also we need to arrange the time. So I would suggest write me an email to explain your situation.
Yeah, I will have to do that and rebook flights.
Just write me email explain because that's why I announced today. Yeah. Normally I only announce close to the final exam.
Better you do it now.
Yeah.
But because you are not able to move this one, I have to rebook my flights now because it's cheaper to rebook them now than later.
What's your flight? When is your flight?
I don't know. I have like a preliminary after the final week, but I think I can rebook it for free so far.
Yeah, then that would be great.
Yeah.
That would be great.
But wouldn't it be possible to just take this one and have
that would have to depend on the progress. That's why this optional can be considered as if I cannot make it the progress, then if I can
need it.
If I can make it progress for sure, I can move earlier.
But my proposal, you don't have to agree. I'm just saying it, and if it's okay, if it's not okay, it's fine. My proposal, you take this optional class, put it on 6 p.m. this day. Optional class 6 p.m. on the 1st of June, and then you can have a final exam on the 8th of June.
Okay, I will think about it.
Yeah, think about it. And,
First, just write me email for your request.
Okay.
教授你好，我想要加签这堂课。
前3的，可是前3可以选这门课吗？
前3
可以吗？可是前3不是没有任何的。
没有，我们是需要再去签额外一张单。
对，可是前3不是希望就是找前3的老师上整个。
你说半导体？
对，因为有重复课可以在前3。
对，但是他们今年没有开营。
哦 ，OK。后来找谁？哦 ，OK，在做一个领导的领导证。What's your department? Oh, okay. You are master or you just arrived? 好，你可以啊。那其实你只要写信给我就好，我就把你加到。哦，好。Hello. How are you? Okay. 对。
那因为那个校际学生今天才开放，所以我
你可以
还没有。
寄那个电子档，直接电子档。
好，那我到时候来给你写。
之前有说过类似的。哦，你说什么 ？OK， 那应该没有。哦 ，OK。为什么就是这个我先你们进入的？
就是可以拿一个渠道。
哦，所以说这样可以拿去。
对，一个
OK， 好，谢谢。哎，你说什么？你是什么？哦 ，OK。对，就看了一下，基本上是发财。哦，没有，我就基本上每个章节是我决出来。对，我那基本上对应章节。哦 ，OK， 我签到了。
Sorry, can I ask you something about this?
Yes.
Two pages is one sheet of paper.
A double side. Yeah, you can write everything. So basically, you have the full page, full sheet. You can write.
Just one.
Yes.
And just don't understand about this makeup.
This is because of I will not be available for lecture on this day. So then these lectures will be shipped to this timing for the makeup.
是材料系的。This you just contact me. I will reply you. Yeah.
New student here.
Yeah. So when did you arrive? Just a few weeks.
12 February. Before the lockdown.
Oh, okay. But how do you know the NYCU? You have any friends who recommend you?
I enjoy the education event in Thailand. They have.
Oh, okay.
They
And then
advertise
where is your university? Your university is in Bangkok.
near Bangkok. SW.
Oh, okay. So I will look at and let you and reply to you. Yeah. Maybe we need to. Probably not this week. This week I will be busy, so I will write mail and then we can make appointment next week. Yeah.
Thank you.
这干嘛？不要放。 Okay. So today we will continue to introduce a semiconductor, but it would be good to know what has happened in the last several decades. So it's good to review the past and also have a little bit outlook for the futures. So now we come to the most basic questions. What is exactly a semiconductor? So if you try to look at the name of the semiconductor, is actually as a name that both combine as a conductor, but also with the name of the semi. So therefore, based on this name, you should start have the feeling that the semiconductor, which is a kind of a conductor, but only have the kind of the half property like a conductor, because the semi, if you look at the dictionary, that the semi normally means as a half. So that means that this is a conductor that only has a half conductor characteristic. So therefore, the semiconductor is a material that is partially conductivity. And to understand semiconductor, we also have to go to the other the very basic materials that we all know that in the material we have the conductor, which has a very high conductivities, and also we have on the other hand we have the insulator, which has a zero conductivity, which has a very high resistivity. So the semiconductor is actually as a material that between the conductor and the insulator. So that's why from the name of the semiconductor, you should already get a sense this is it's similar to conductor, but only have the half property like a conductor. So for example, we have the silicon, we have a germanium, and so on and so on. And the most important characteristic is not just because of conductor. Semiconductor is a partially conductivity. The most important property for semiconductor is that this conductivity can be modulated by the temperature or voltage. So that gives another flexibility to control this material, because either we give the temperature, we give the additional bias, it can be more like a conductor. But if we didn't give the bias, it can be more like an insulator. So that can give us a certain freedom to control the material property. So if you consider as a simple example, like the conductor is a faucet that always open, 水龙头 is a faucet that always open, and insulator is a faucet that always completely off, completely shut. And then the semiconductor is something that you can control. You can turn on and turn off as we need it. So that's why the semiconductor can become as an electrical switch, because we want to have the property that we want this material operation, we can easily turn on. We don't want this material operation, we can easily turn off. So we can control. So in the end, the semiconductor become as an electrical switch. So what is a semiconductor? A material between the conductor and insulator is a partially conductive, and then its conductivity changes. The conductivity change with the temperature and voltage. And why are the semiconductors so powerful? Because it's highly controllable. So the conductivity can be switched on and off as we prefer. And therefore, the semiconductor can act like an electrical switch. So the electrical switch is the foundation of the transistor and the modern electron. This function that the semiconductor enable for electrical switch, that's become the general purpose why we need a transistor being used in the modern electronics. And then compared to the electrical switch, I think that nowadays daily life, what we normally use is a mechanical switch, like the turn on the light, turn off the light, like the somewhere the turn on, turn off. That's a mechanical switch. It is mainly based on the mechanical to connecting or disconnecting. But the problem for mechanical switches cannot be go very fast because it always has a limitation of this mechanical. But if we can make it as an electrical switch, we can make it as a very fast, we can make it as a very small. And also if we can reduce the operation voltage, then we can make it as a switch very power saving. That's the general goal. That's why the semiconductor materials are so attractive and then so amazing, because we can use this as an electrical switch to enable for the high performance product rather than use the old very conventional mechanical switch. So if you look at the semiconductor industry outlook, every certain timing, there's always a semiconductor booming by the certain application, and then the application not at that moment become the main driving force. We need to develop more and more advanced semiconductor. For example, in the 1990s, the main driving force for semiconductor industry is because we were in the age of the personal computing. Due to the personal computing, people realized that if we want to have a very good PC, high performance PC, we need to have very good semiconductor. So that's in the 1990s, that's a main driving force for semiconductor. In the 2000s, there's another driving force to make the semiconductor technology booming again, which is internet. I think it's no doubt that the internet is also the one of the key enablers that we need to have lots of the high performance semiconductor technology to make us has a very fast internet, can be connected every time, everywhere, and the most important, it has to be the very low power consumption. That means we can connect this internet without lose our energy, lose our battery energy. So that's also another booming for the semiconductor industry. And then in the timing of the 2010 to 2020, the main push for the semiconductor industry growth is due to the smartphone. I think that's also there's no doubt that the smartphone, that it's a kind of the engineering miracles that we put millions, billions of transistors inside the small cell phone cases, and that can enable us a very, very amazing function that we can have the watch the video, we can have the Wi-Fi, we can even use a cell phone to do some calculation, to do some computing. So the same smartphone becomes one of the key driving force. And then beyond the 2020, for sure, that's artificial intelligence. Artificial intelligence is also another engineering miracle that we put all of the best technology together. In the end, we can enable this high performance computing. I think nowadays, everyone definitely cannot live without the AI. We use the AI for the many help that give us to accelerate our working efficiency, even help us to address the daily life, the issue. So I think that's all being enabled due to this artificial intelligence technology. And then for this, up to the 2030, we might reach for 1 trillion transistor. So the semiconductor technology can be continuous growth because of this new application. Also beyond the AI, we have several still the lots of new technologies that are still waiting for us and still waiting for everyone's effort to develop, to production, to refine it. For example, we have the humanoid robot. That's also the technology that the people put a lot of expectation for the robot. And then also we have this driverless electrical vehicle like the robot taxi that we have enabled that there's no driver, but that already can help us for the taxi function. And also these all need a very advanced semiconductor chip. And also we need to have the certain, like in the last year, I think one of the most hot topic that the people, in the beginning, you might think this is not possible, but in the end, you think it can be realized in the next 10 years. It's what we call the space data center. So you know that nowadays all the data center on our planet, on our Earth, but on our Earth we were suffering several issues. First, we need a lot of power because the data center is kind of like it's a very hungry for power. You need a lot of the nuclear plant to try to support this data center. So we need a lot of power, and we also need a very advanced cooling, and then we also need a lot of the space that we can build up for the AI data center. But therefore, there's also as a discussion that how about we put the data center in the space, because in the space we will have the endless solar power. All the data center can be powered by by our sun, by the solar power. And also in the space we don't face any cooling issue because space is already the very cold place. So we don't need any advanced cooling. So that, and also in the space we don't face any issue for any place that we can put it for this data center, because the space is very huge. So therefore the space data center can be the very interesting technology that in the end to keep booming the semiconductor. Imagine that if you need to have the data center in space, what's the component you need? For sure you still need a high performance chip, but this high performance chip need to be the radiation hardness, because in space we have a lot of radiation. And also these high performance chips need to be tolerant for the high temperature, extremely low temperature, and we also need to have this very fast communication between the space and down to the earth. So that's why we need to have this very amazing communication. So these are all the possible to keeping driving our semiconductor industry. So here, this is something that is sharing by the TSMC, that how their technology start to enable for the NVIDIA GPU. So you can see that everyone start to getting more familiar with the NVIDIA, probably just in the last couple of 3 or 4 years, starting from 2020, 2021. But you can see that beginning in the 2018, TSMC already start to work for the NVIDIA. Let's already have this N7 for this NVIDIA V100. And until right now, we have the NVIDIA Blackwell. And then that's all enabled by this very advanced technology. So currently, all AI customers are working with the TSMC on GPU and ASICs, and majority of AI accelerator demands is on the 3 and 5 nanometer. Also, beyond the data center, for our daily life, we still need a lot of semiconductor to enable or for the application that we are using every day. For example, inside the automotive, we need to have the semiconductor toward smarter, safer, and greener here. So the other major growth driver identified by TSMC, this is information shared by TSMC last year, is automotive. So in the automotive, the main needed for semiconductor is because we need a computer is also being we need a lot more sensor and computing power. Because if we want to toward the level 3 to level 5 self-driving, that means we need to place more sensor on our car. We need to have more good computing that allow the car to identify the environment that is nearby. And also, as mentioned here, using the 3 nanometer for automotive computing and 12 nanometer for the NYCU microcontroller unit, it's another growing business so far. So these are the latest information, but now it would be good to look at the history, how the history lead us from the very beginning till so far. In the semiconductor, there's too many important innovations. It's difficult to summarize, but I refer to the Dr. Morris Chen, his talk in the 2018. He listed the 10 most important innovations in the semiconductor industry. I think with no doubt that from his point of view, these 10 definitely can be the most critical innovation that lead to us to nowadays we have this amazing technology. The first one is a transistor. That's starting from 1948, and then the first one was coming due to the Shockley Bardim that coming from the Bell Lab. So that's the first demonstration of the transistor. But the first demonstration of transistor is not done on silicon, it's done the germanium. So later in 1954, we start to have the silicon transistor. Silicon is one of the most abundant material on this planet, so we can easily get silicon, and then the cost also a little bit cheaper, and also most important is the silicon. Later we will talk about the silicon has a very unique property to grow the negative dielectric as a silicon dioxide. But anyhow, in 1954, silicon transistor had become as a second major innovation. And then in the 1958, we start to have the concept of the integrated circuit IC. That's proposed by the Jack Kilby from the PI. Jack Kilby was a previous colleague with Dr. Morris Chen. They worked together when they was in the TI. So that's also the very good to know that the Morris actually he witnessed the whole semiconductor from the beginning of the transistor till nowadays for the AI application. So in the 1958, the Jack Kilby demonstrated the first integrated IC that we call the integrated circuit that we call the IC. And then in 1965, the Gordon Moore was later become the co-founder of Intel, but at the moment was mainly working for the Fairchild. So the Gordon Moore proposed the Moore's law. So the Moore's law is a kind of the empirical indication that the density of our chip should be double every 2 years. And then later we will talk about this for the Moore's law. Starting from 1964 and later, we start to have the MOS technology. That's including the MOSFET. Before the MOSFET, we mainly use the bipolar transistor technology, but later, starting from 1964, we start to have this MOSFET technology, and also one of the key reasons why the MOSFET is so robust till nowadays is because of MOSFET can have this silicon dioxide gate. And also later, the professor in the NYCU, Professor Sa Zhitang, who proposed as a CMOS, which is combined as a PFET plus NFET, and now the CMOS becomes the foundation of all of the advanced logic technologies. And later, starting from 1966, we start have the technology for the memory. That's including, for example, the DRAM and flash. And for sure, when we talk about the flash memory, we have to mention the Professor Simon Sees, who was the emerite professor, honorary professor in the NYCU, but was passed away several years ago. And then he proposed, with his colleagues, can propose as a floating gate memory, and now become as one of the successful product in the industry now. And also, starting from 1960, the companies start to realize that they cannot work everything by themselves. They cannot. They have to make a material, make a semiconductor. They can to make the testing, but they decided to outsource of this assembling test. Outsourcing of the assembling test. And in the 1970s, Intel started to demonstrate the microprocessor. And then starting from the 1970s, we start to have the VLSI system. And then because of this consideration of the VLSI, very large scale integrated system, then we start to have getting more and more the fabless company. So we have the company who dedicate for the design, and then we have a company dedicated for the semiconductor. This is because of due to the VLSI system, and then we realize that if you want to design, you have a system level, you need to have a dedicated efforts. And since 1985, because of this development of the VLSI system, and then the rising of these fabless companies getting more and more, and then the fabless companies start to need to find the company who can manufacture the chip for them. Therefore, in the 1985, Dr. Maurice Chen started to bring out as an idea that we need to have the dedicated foundries. we need to have a dedicated foundries that for these fabless companies. So then on one side, this foundry, they just focus on the technology, they focus on the process, they focus on the help to the customer to enable their design. And then fabless company just focus on their design. So then this working model become as a main business, like the development, and then the main business innovation since the 1985 so far. That's why we start to have this dedicated foundries. So if you look at what happened nowadays, and then you back to the 1985, then you will feel very surprised at how the Morris at the moment foresee this business can be grown like nowadays. Become the foundry become as a national core technology for every country. They all want to have the dedicated foundries. Okay, so then let's go to some old picture to understand what has been done in the past. This is first integrated circuit. So invented by the Jack Kilby on the 1958 at the Texas Instrument, and first time to complete circuit was built on the single chip. Although right now it looks like it's very rough, it's just like it looks like it's a very rough material, but actually it's already combined several components here. So the Jack Kilby's breakthrough is mainly combine all components on one material. That's nowadays we call as integrated circuit. It's a simple idea, but it has a huge impact on the whole semiconductor industry. And this is this image captures the historical moment when the human first miniaturized every component and made it on the same as the entire circuit. So what is Moore's law? So Moore's law is observation. It's not the equation from the derived. It's not and doesn't have any physical base. Didn't have any physics-based equation. Didn't have any very rigorous calculation. It's mainly coming from the observation that the number of transistors will double every 2 years. So the Moore's law means that the number of the transistors on computer chip roughly doubles every 2 years. Because ideally is that the more transistor they are, the more powerful the chips become. So that's why in the first slide I showed that right now if you look at the A19, there's already more than 25 billion transistors. And then we expect that up to 2013 we have more 1 trillion transistors. This idea is because we put more chips, then we put more transistor, we have a more powerful the chips can have. And this is Gordon Moore, who is a co-founder of Intel. He proposed this observation in 1965. It's a very visionary proposal. And then I think he didn't realize that in the end it's become the golden rule for semiconductor industry. Even nowadays, we still try our best to keep the Moore's law alive here because we want to fabricate the transistor to follow in this Moore's law here. So why this is important? This law helps us understand why technology has advanced so rapidly. in the past, it's a one computer used to occupy an entire room. But nowadays, it's a cell phone that has 100 times more powerful than early machine. And this is because we have more and more transistor to be packed into a smaller and smaller chips here. That's why our right now the chip is so powerful. And Moore's law has accurately predict the pace of the technology advancement over the past 50 years. But still so far, we actually still can try to catch Moore's law with several technology innovation, including the DTCO, including the FinFET, into the nanosheet, and so on and so on. So here is the same one that we have been shown previously, that how the industry try to follow this Moore's law and what's the innovation here. So as we previously already mentioned, the first one is equilibrium scaling. We shrink the transistor and pack them more in the density inside the chip. And then the main innovation is strength silicon, high K metal gate. So that's in the timing around 2010. So that's equilibrium scaling. We have started to employ the high K metal gate. We start to have this strength silicon. And later, when we talk about new transistor and new materials, that's including as a FinFET, EUV, high mobility channel, and also the DTCO. So every part plays a key role to keep our semiconductor technology follows Moore's law. And then the future trend will be, if you look at this chart from 2013, that's the latest information. This is information coming from 2024. Here, by around the 2013, we should have the 1 trillion transistor. And right now, if you look at the latest iPhone 17 is based on the N3 technology, and then the next generation will be the N2 or N2P, and then we plan to have the production around the TSMC might have a planned production in the next years. So you can imagine that the chip as a factory, and then each transistor as a worker. That's why if we get in more workers, ideally we can get more productivity. We can have a more high performance because our workers, that we get more like someone who can help. That's why we want to have more transistors. So if we pack more workers into a small space, but we also need to maintain, we also need to making them faster efficient using the less power. So in the end, you can realize that actually what the humans doing is just trying to bully this worker, this transistor, because we want to pack more workers in this room, but we provide them less food. We want to then work harder, we want to then work more efficient, but we don't want them to eat lots of food, because the food means the power consumption. So then this is how our transistor and our chip is doing now. We have more 20, 30 billion transistors, but in the end, what we want to have a low power consumption, because the low power can save energy. We provide less power, we provide less food for them. So in the end, just kind of like in this scenario, we want to get in more, but we provide we also want to let them to consume less. Okay, but we still need to go back to the very fundamental, see that how the microelectronics evolution from early time till now. The early time, the first one we use is a vacuum tubes. Used in the early TV, radio, and radar system, but the problem for vacuum tube is very huge. Then therefore we need to have a lot of space to storage this vacuum tube, so it's not a very good technology. And later, starting from 1947 till 1980s, we start to leverage the bipolar transistor. And later, from 1960, MOSFET becomes the main dominating technology, because the MOSFET is a small, fast, and energy efficient, and therefore the MOSFET becomes the foundation of all modern computer and then the smartphone chips. Therefore, we also need to start to see that we have MOSFET, but what else the new things to bring us to here? As I say that in the early time we have many innovations here, and the first one is what we try to increase our current. If we can increase the current, then we can also increase the performance. So the first ideas that we hope to achieve is that we want to have the mobility improvement. Because of if we can find a new material that gets a higher mobility, that means our transistor can deliver a higher current. So the current is getting higher. Normally, it's also suggests that the transistor, the system can have a higher performance. And why the mobility is crucial to improve the transistor current is because of if you have followed, we will also talk about this equation later, but if you have followed the electronics, basic electronics, you should be aware of that. The saturation current is proportional to the mobility oxide capacitance VGS minus VTH squared. So from this equation, we can simply know that as long as mobility increase, our output current is increased as well. So that's why we have a strength silicon, germanium channel, 3-5 material that's mainly trying to let us have a higher mobility. And later, as you know, that one of the key trends for semiconductor is trying to do the scaling. So the scaling means that we try to make everything smaller. So imagine, let's just use a MOSFET as an example. Imagine this is a typical MOSFET structure. So this is the second time we draw the MOSFET. That should be everyone should a little bit familiar. So we all know the MOSFET has a region where we call as a gate. In the left hand side, which is a source. In the right hand side, we call as a drain. And normally we will define the region between the source and drain under the gate as a channel length. So that's we call as a LCH, channel length. And then if you consider the channel length is pretty large, this is a case we call as a long channel device. And if you try to imagine that the long channel device characteristic, which will be shown in here, because this is a long channel device, this is a very regular device, so therefore we have a normal IDVG, and here I plot as a log drain current versus a gate voltage here. And then for the normally for the long channel device, we have this kind of a characteristic, something like this one. And long channel device normally has a lower current, lower off-state current, lower leakage current. So for example, we might have the current down to 10 to minus 12. At the meantime, this is a similar, when we increase the gate bias, beyond a certain value, the current is increased. And then we consider this turning point as a threshold that the voltage need to larger. Therefore, we call this as a threshold voltage. If you don't understand threshold voltage, that's fine. Later we will explain more detail. But here, I just want to illustrate that these all are the key characteristics that we are caring about. So that's a value we call the threshold voltage. So that's a typical characteristic for the long channel. The reason why I say the long channel, because later I want to illustrate another specific case, which is a short channel device, short channel MOSFET. Imagine if you try to scaling the transistor, for sure that we will also make the channel length, LCH, as smaller as possible. So for the short channel device, we can expect this will be still the same. Oxide dielectric here, gate metal here. And this will be still the gate and source and drain. But now the source and drain are bring so close. So that's why we call this as a short channel device. But now we start to face one problem. It's because of the short channel device. as you see the low channel device, the electron, if you still remember the previous discussion how the MOSFET turn on is that the electron will flow from the source to the drain. So normally the electron will be stay here, and then we give the gate bias here larger enough, we have the electron accumulating, we apply the VD bias here, and therefore the electron will start to flow to this region, right? So that's become our typical IDVG characteristic. But because this channel length is so wider, so long, so the electron here cannot easily to come to this region. It must be needed the help from the gate to form these electrons. But think about, if you bring this so close, there's a chance electron here can go through from the source to a drain, even without bias, which means this one can go through here, this one can jump to the drain side, and this one can jump to the drain side. Of course, we have a physics to explain this. This phenomenon we call the tunneling. And to understand the tunneling mechanism, we need to have the quantum physics. The main difference between the Newton physics and quantum physics is Newton physics tells us if you throw the ball against the wall, you will see only the reflection. So if you have this, this is your wall, 墙壁. If you throw a ball against a wall, based on Newton physics, there will be only the one scenario happening, reflection. The ball will be rebounds. This is by the classical Newton physics. And why we need the quantum physics semiconductor? Because from the experimental data, we see this one is getting smaller. The electron can have chance to across this wall, reach to the other side. So normally we will see the short channel device suffering high current here. And this one is normally we call as a off current. And then we see the short channel has a very high of current. Which is something we don't want it, because that means your transistor, your cell phone in the idle, you don't turn on, but you already have a high current, and then this high current will cause you lots of power consumption. So we don't want it. Of course, short channel device has a certain aspect, has a certain advantage, which is can improve the on current. So the ion can be improved. This is a short channel. That's why to make us a short channel transistor is always as a trend, because we want to have a higher on current. And reason why the on current is higher because of current equation. This is W over L. If you make this smaller, the current is also getting high from the very basic equation we already can see. But we're always suffering this higher on current. So in the beginning, the first task we want to address is we increase the on current. But later we realize that if we make a short channel device, we cannot only see the on current, we also have to consider the off current. So therefore, the overall goal is become on over off. This kind of ratio. Because we want to make sure this ratio as a larger as possible, because if this one can be larger, that means we have the device very beautiful, has a high on current, low off current. So therefore you will see later we are not only consider I-on as a criteria, we consider I-on over I-off as a criteria. And back to here, in this one, if you use the Newton physics, there will be only one scenario that the balls will be rebounds. But this cannot explain what's happening in the semiconductor. That's why we have to introduce as a quantum physics. We have to introduce a quantum mechanics. The quantum mechanics for sure is a very complicated subject that some of you might spend like the 1 semester, 2 semesters to understand quantum mechanics. But the good thing for the semiconductor is that we don't need that difficult. We only need the most basic part to understand the tunneling. Because based on the quantum mechanics tell us if you have the one ball through the wall, you still will see the reflection. But also you were able to see as a tunneling. So you are able to see your balls can penetrate the wall and reach to the other side. This is the reason why we need a quantum mechanics to understand this phenomenon. Many of you, when you start to learn quantum mechanics, you will feel confused because quantum mechanics is probably in the chapter 1 or 2. But MOSFET is in the chapter like 10, 11. So you don't connect with each other, you will get confused as to why we have to learn this. But now, I hope this way you can connect the later from the device operation to the beginning of this physics. The main reason is that this tunneling cannot be explained by the Newton physics, can only explained by the quantum mechanics. That's why we need to have the quantum mechanics to help us to figure out our understanding is correct. So this is based on the quantum physics or quantum mechanics. And then actually it's the same, it's called the tunneling effect. So that's why the quantum mechanics is pretty crucial in the later part. Okay, so now we understand that in the first test, what we are trying to do is to improve ion. But we will realize that only consider ion is not enough. We need to consider the on versus off. So that's why in the advanced technology, we actually interested in is on over off. And then we have the specific, more professional name to talk about the on-off current. Sometimes we call it on-off ratio. That's a pretty like the typical term that everyone accepts. But sometimes we use a more professional term to talk about on ratio because the on ratio is mainly considered as an electrostatic improvement. So we want to have an electrostatic improvement in the end to increase ion, but also decrease I-off. So with this consideration, let's bring us to the new device architecture. We start to have the SOI, silicon on insulator. We start to have a FinFET. We start to have a nano wire. These are the reason we develop these advanced in because we want to have a better control the carrier below the gate. We don't want to have this tunneling effect. We want to reduce off, but at the meantime we want to increase on current here. So the last one, this one surrounding gate, this is just the same as what we generally call as a Gate-All-Around. And because of the Gate-All-Around, so we start, because of we mentioned for the on-off, And then current ratio, we talk about FinFET, so therefore we have to introduce the Professor Tian-Li Wu and for his FinFET innovations here. So Professor Tian-Li Wu is from the UC Berkeley, and now he's also the chair professor at the NYCU, and then he is known as father of the FinFET. And then you can see that in the middle, this is our typical transistor MOSFET that we have been shown. And then because of this is electrons here. And once we apply the gate bias, and we apply the drain bias here, then as we previously discussed, the electron will be flow from the source to the drain and become as a drain current. Just be clarified that I'm talking about in the angle of the electron current. The electron is flowing from the source to the drain, and that's become electron current. But in most of the typical standard, if you look at the electronics textbook, they talk about the current. The current is the opposite direction of the electron current. So therefore, you will see the most of textbook, they will say the current is flow in this direction, because they are using the angle of the current, but I'm using the angle coming from the electron current. And the reason I prefer to use the electron current because that's more physics, makes sense. So electron current is flow from here to here and become the drain current here. And because of this device, you see this and this are in the same plane. So that's why we call this as a flat or planar transistor. But if you consider the FinFET, it's actually as a 3D structure where your gate has a 3-dimensional drop off above your channel. Your channel is here. This is your source, your drain. And previously, we can only control the electron in the top, but now we can control the electron in the sidewall. So we have a 3-dimension control. So therefore, we can consider this as a vertical transistor, and therefore the gate here drops around the channel on 3 sides. And then therefore you can consider the FinFET is like a 3D version of the faucet. Because now we can control not only from top but also the sidewall. So that's the main idea that why the FinFET become the very important technology. And why I call it fin? Because of this structure here. It looks like the fish fin. So if you don't know what's a fish fin, just Google it. You will see the lots of the fish fins. So that's why we call this as a FinFET. And the first paper where Professor Tian-Li Wu published is a paper from 1999. As you see that this is the first experimental demonstration of the FinFET, where we have a 3-dimensional wrap out our channel, and then we can achieve. And again, that's why I say the IDVD is always very critical, in this paper, the most important is this IDVG curve. IDVG, and then also again you can see that from 1999 till 2026 how we care the electrical results characteristics are the same. We still care about the substrate sweep, which is the same like the TSMC 2 nanometer paper. This one, this is our substrate sweep, and this is a first demonstration, but at the moment was demonstrated as a PMOS. So that's why you see the current is in another way compared to the NMOS. But the idea is the same, no matter for NFET or PFET, that once we have the FinFET, then we always have a better electrostatic control. Okay, I think we can stop here because the rest of will be certain that the option beyond the FinFET and the new technology development, so we can leave those in the next week class. So we will be ending out the class today. So if you have any question, just feel free to let me know. So see you guys next week.